Welcome to Advanced Learning Tutoring. This is the chemistry playlist. Please like this video and subscribe to our channel. Pure substances and formulations. A pure substance is a single element or compound not mixed with any other substance. For example, pure water only contains H2O molecules. To distinguish between a pure and impure substance, melting or boiling points can be tested. Pure elements and compounds melt and boil at specific temperatures. For example, the boiling point of pure water, H2O, is 100 degrees Celsius. Melting and boiling point data can be used to distinguish pure substances from mixtures. Impure substances will melt or boil over a range of temperatures. Use an apparatus, a capillary tube, to test the boiling or melting point of a substance using a thermometer. Compare this to a data book or the internet value for that pure substance. A formulation is a mixture that has been designed as a useful product. Many products are complex mixtures in which each chemical has a particular purpose. Formulations are made by mixing the components in carefully measured quantities to ensure that the product has the required properties. Formulations include fuels, cleaning agents, paints, medicines, alloys, fertilizers, and foods. An example of a formulation I like to think of is Calpol, the pink sugary medicine designed for children. It contains the drug, it contains a pink food colouring and lots of sugar to make it desirable for children. Paper chromatography required practical. Chromatography can be used to separate mixtures and give information to help identify substances. Chromatography involves a stationary phase, typically paper, and a mobile phase, a solvent. Separation depends on the distribution of substances between the phases, i.e., how soluble each component is in the solvent. If the substance is very soluble, the component travels further up the paper. If the substance is insoluble, the component remains on the start line. A typical example that can be done using paper chromatography is to use inks, and you dip this into your solvent, typically water, and it will separate that ink into the component colours. The ratio of the distance moved by a compound, measured from the centre of the spot to the start line, to the distance moved by the solvent, or the solvent front, can be expressed as something known as the RF value. Different compounds have different RF values in different solvents. This can be used to help identify the compounds. The compounds in a mixture may separate into different spots depending on the solvent, but a pure compound will produce a single spot in all solvents. Paper chromatography exam style question. Typically, exam questions on paper chromatography will display an image with some errors on the equipment. The first question we see is to identify two mistakes the student made when setting up the experiment and explain what problems one of the mistakes would have caused. Now, the solvent can be seen as above the start line, and the start line is labelled to be drawn in ink. These are mistakes. The start line needs to be drawn in pencil, as the ink line would run up the paper as would dissolve in the solvent. The water or solvent level must be below the start line, otherwise the colouring would dissolve in the solvent. Calculating an RF value. RF values are calculated by doing the distance travelled by the substance, divide that by the distance travelled by the solvent, or up to the solvent front. You measure from the centre of your dot down to the start line, and from the solvent front down to the start line. Divide these two values and you have your RF value. RF values are useful in comparisons. Explain how different dyes are separated by paper chromatography. A solvent moves through the paper. Different dyes have different solubilities in the solvent, and therefore different attractions for the paper, and are so carried different distances. Identification of common gases. It's typically very difficult to identify a gas because you cannot see it. Hydrogen can be tested when a burning splint is held at the open end of a test tube, and hydrogen will burn rapidly with a squeaky pop sound. To test for oxygen, a glowing splint is inserted into a test tube of the gas. The splint relights in oxygen. To test for carbon dioxide, an aqueous solution of calcium hydroxide or lime water is used. Carbon dioxide is bubbled or shaken through lime water and the lime water turns cloudy. To test for chlorine, damp litmus paper is put into chlorine gas. The litmus paper is bleached and turns white. Identification of ions. Testing for cations or positive ions. Positive ions are typically metal ions. These metal ions will be found in ionic compounds. Note that this is the test of the ion, not the metal atom. Flame tests can be used. Nichrome wire is dipped into concentrated acid. The wire is then dipped into the solid metal salt and placed into the hottest part of the flame. If a sample contains a mixture of ions, the flame colour can be masked. Lithium ions give a crimson flame. Sodium ions give a yellow flame. Potassium ions give a lilac flame. Calcium ions give an orange red or brick red flame. And copper 2+ ions give a green or turquoise flame. You can also use metal hydroxides to test for the presence of metal ions, based on the metal ions forming a precipitate of different colours. Sodium hydroxide solution can be added to some of your metal salt to form your precipitate. When calcium 2+ ions react with your hydroxide, you form a precipitate of calcium hydroxide. Calcium hydroxide is a white precipitate. Similarly, with magnesium and aluminium ions in sodium hydroxide, you produce magnesium hydroxide or aluminium hydroxide. Both are white precipitates. To distinguish between your calcium, magnesium and aluminium ions, you could carry out a flame test to show the identity of your calcium ions. Magnesium ions do not produce a significant coloured flame. So to distinguish your aluminium ions, you add excess sodium hydroxide. On the addition of excess sodium hydroxide to your aluminium hydroxide precipitate, it will redissolve. The presence of copper ions with hydroxide produce a blue copper hydroxide precipitate. To test for iron 2+ ions, it will produce a green precipitate of iron hydroxide, which will gradually turn brown if allowed to come into contact with air due to oxidation, which is the loss of electrons. And iron 3+ forms a brown precipitate of iron hydroxide. Identification of anions. Anions are the negative ions found in your unknown ionic compound. Typically, your ionic compound will be a white solid. So we do chemical tests to identify the metal and the non-metal ions that make up the unknown ionic compound. The anions or negative ions we test for are carbonates, halide ions, and sulfate ions. To test for the presence of a carbonate, react the salt with dilute acid. This will produce carbon dioxide gas. Bubble the gas produced through lime water, and if it goes cloudy, you know carbon dioxide was present, and therefore the anion was a carbonate. To test for the presence of halide ions, in solution it will produce precipitates with silver nitrate. Add silver nitrate and dilute nitric acid to your unknown ionic compound. The reaction will produce either silver chloride, silver bromide, and silver iodide, each giving different coloured precipitates. Silver chloride is white, silver bromide is cream, and silver iodide is yellow. To test for sulfate ions, use a solution of barium chloride in the presence of dilute hydrochloric acid. In doing this, the sulfate ion reacts with the barium ion from barium chloride solution to give a precipitate of barium sulfate. Barium sulfate is a white precipitate. Instrumental analysis. This includes flame emission spectroscopy. It's an example of an instrumental method used to analyse metal ions in solutions. The sample is put into a flame and the light given out is passed through a spectroscope. The output is a line spectrum that can be analysed to identify the metal ions in the solution and measure their concentrations. This is done by comparing the line spectrum to the line spectrums of those identified known metal ions. Elements and compounds can be detected and identified using instrumental methods. Instrumental methods are accurate, sensitive, and rapid. Being a sensitive method means that you only have to use small amounts of your unknown element or compound.